Okay, so we're studying particles in the gas phase. We know that particles in the gas phase will spread out to fill the container. And so that means we can measure the volume of the sample of gas by the volume of the container. We also figure they move pretty rapidly and continuously, rapidly compared to liquids and solids. And we can measure temperature to determine some sort of average speed at which they're moving. And the faster they move, the more energy they have. We know that if they're moving continuously, they're certainly going to collide with each other, and they'll collide with the container and exert a pressure. And it's also important to measure how many particles are trapped in a container, because of course that affects the pressure. So we have these parameters to measure for a sample of gas. And we found in last class that the volume that the sample of gas is taking up is inversely proportional to the pressure it exerts if you maintain the same quantity of gas particles and to maintain the speed, maintain the N and the T. So that's an inverse proportionality. We also found from class that volume of a gas is proportional to the temperature, directly proportional. And that is if you maintain a constant sample, if you don't want to add or subtract any, and the volume is proportional to temperature in order to maintain pressure, both internal and external. And so this is actually called Boyle's law. And this one is Charles' law. I mean, not that you need to know that. And Avogadro, not to be outdone, Avogadro, there we go. He noticed, as many others, that volume, the space a sample of gas takes up, is proportional to how much gas you have in order to maintain the temperature and the pressure of that sample. And in fact, in that direct proportionality, if you map those, it's wonderfully linear, like 1 mole, 2 mole, and then that 1 mole turns out to be a volume of 22.4 liters per mole at STP conditions. And so if the external pressure is 1 atmosphere, we are also saying the pressure of the gas is equal to that external pressure. So 22.4 liters per mole. Now, STP, we usually think of the pressure as 1 atmosphere. Technically, it's slightly different. It's 1 bar. We'll just go ahead and use atmosphere. They're pretty similar. 1 atmosphere is 1.013 bar. Just keep in mind, you might encounter bar as a measurement. Okay, so what we're going to do now is take these 3 observations and put it all together. If volume is inversely proportional to pressure, but also proportional to N and T, we're going to put that all together. And then we could take our proportionality and turn it into an equation. Like these 2 sides aren't equal, they're proportional, but they could be equal if we offset them with some kind of constant that we're going to call R. R. R is this proportionality constant. And so we have to figure out what that is. We're going to call it the universal gas constant. Universal means any gas, and constant means no change. And we can figure out what that is if we take some data, like this data right here, this 22.4 liters per 1 mole, this molar volume. We can figure out what it is by saying, okay, take this relationship. I just took my pressure, multiplied both sides by pressure. So I have PV equals, and then I just switch the N and the R, nRT. And if I have 1 mole and STP conditions and this molar volume, the 22.4, and I plug all those in to this equation, and by the way, I want to plug in Kelvin temperature here, 1 mole there, then I can calculate R. This is based on experimental measure, and I can calculate R, this constant of 0.0820. I could get more digits here if I have some more digits on this volume measurement. And then it has interesting units, pressure and volume and mole over temperature. None of those units cancel. So I end up with liter atmospheres per mole Kelvin. So here's our R value in these particular units. I mean, last semester, we actually worked with this gas constant. We called it the ideal gas constant, and we had it in different units. We had it in joules per mole Kelvin. Yeah, you can change liter atmospheres to joules. It's another R, but right now for the gas laws, we'll leave it in the pressure volume units. And in fact, in your next lab experiment, you will measure mole, temperature, pressure, and volume and calculate your own R. And hopefully you will get something very similar to this. You will determine the value of this proportionality constant by experimental determination. So this whole PV equals nRT, it's referred to as the ideal gas equation of state. It's an equation that describes the behavior of the state of gases. So we just calculated R for 1 mole of a gas at STP. So follow up in the next video.